Welcome to Module 1.1.1. We'll start with some algebraic operations. These are very foundational, things you might already be familiar with. But I'll reintroduce some fundamental theory, and we'll do just a couple basic examples to refresh our memory on these things. Let's start with the order of operations. Very, very basic stuff. All this tells you is when you're given many different mathematical operations, for example, exponentiation, or multiplication, division, addition, subtraction, what order do I perform them in? This might seem like a simple question, but unless we as thinkers establish a systematic way to do this, it becomes ambiguous. So there's a canonical order in which we follow. It goes like this. We start with anything in parentheses. Then we move on to anything that's being exponentiated. Then we do multiplication followed by division, and lastly addition followed by subtraction. So PEMDAS. Sometimes people use mnemonics for this, like please, excuse, my, dear, D, Aunt, A, Sally, S. So these types of mnemonic devices can be useful, or you can just remember the order. To me, at this point, it's completely natural. But if you're just refreshing yourself on this, the mnemonic could be nice. So let's look at an example of this in action. Suppose we're given an algebraic expression or statement like this that has many different operations in it. We have exponentiation here with the 3 minus 2. We also have some addition with the 2 plus 4, and then ultimately a multiplication all the way on the outside. So we'll follow our order of operations. First, everything in parentheses will be evaluated. So this says I have 2 times, first thing in parentheses is 2 plus 4, so 6. And I also evaluate what's in parentheses in the exponent to the power 1. So I haven't evaluated the exponentiation yet. All I've done is evaluate the parentheses. So now I say, well, what is 6 to the first power? Anything to the first power is just itself. So we have 2 times just 6. Okay, so I'll just say recall that x to the 1 is just equal to x for all x. So remember, raising anything to the first power leaves the thing alone. And finally, I do 2 times 6, multiplication, so 12. So here I saw that first I did what was in parentheses, then I moved on to exponentiation, then I did the multiplication. So let's review another basic concept, which is how to work with fractions. I need to know how to add and multiply them, and also how to simplify improper fractions. So adding is the most difficult. It would be nice if a over b plus c over d was equal to a plus c over b plus d. This is, I think, everyone's 4th grade dream. It is not true. You have to do something more delicate, which is to find a common denominator. That's what we call this b times d, is a common denominator. So what I do is I take a over b and multiply top and bottom by d. And I take c over d and multiply top and bottom by b. This gives me a b times d as the denominator for both of them, and only then can I add. Only once I've found this common denominator. Till then, it makes no sense. Now, multiplying fractions is more straightforward. I'm allowed to just say multiply the numerators and multiply the denominators, and then I'm in good shape. So this is actually simpler, even though in general multiplication is more complicated. So we see here that a over b times c over d is equal to a times c divided by b times d. So product of numerators, product of denominators. Simple. Now the last thing we want to look at is what's called improper fractions, which are just fractions of fractions. So if I have a fraction, a over b, and I divide that by another fraction, c over d, I can simplify this in a natural way so that I remove some of the fractions. This is equal to a times d over b times c. So the easiest way to prove this is just to take a over b divided by c over d, and to multiply first by, let's say, b over b, which is 1, so that this is equal to a divided by cb over d. And then I multiply again by d over d to get AD over CB, or BC. This is just a matter of multiplying by 1 in the form of b over b and d over d. This is a very common trick in manipulating fractions. You multiply by 1, but when it's written as something divided by itself. So let's look at an example here. Real basic stuff, 5th grade stuff here. So what was good practice? So I want to add 12 over 17 and 2 over 3. So I need to find my common denominator, which is just the product of the denominators. So 17 times 3 is equal to 51. So what do I do here? I say 12 times 3 divided by 17 times 3 plus 2 times 17 over 3 times 17. So 12 times 3 is 36 over 51, and 2 times 17 is 34 over 51. And now I add the numerators. And what is 36 plus 34? That is 70, divided by 51. Okay, so again, in order to add the fractions, I had to find a common denominator. Let's look at a more abstract example, where here I don't have concrete numbers, I have two variables, x and y. I can still play the same game. I just had to find a common denominator abstractly. So what's the common denominator here? Well, it's y to the 7th times x to the 4th. So I say this is x squared times x to the 4th divided by y to the 7th times x to the 4th plus y cubed times y to the 7th divided by x to the 4th times y to the 7th. So all I did is multiply by 1 in the form of x to the 4th over x to the 4th, or y to the 7th over y to the 7th. And now I clean up. So what is x squared times x to the 4th? We will review this shortly, but this is x to the 6th. I add the exponents. Plus y cubed times y to the 7th is y to the 10th. And then downstairs I get, let's rearrange as x to the 4th times y to the 7th. So in this case, to compute this or simplify it, put it under a common denominator, all I have to do is figure out what that common denominator is. And then I can add the new numerators. Okay. So let's talk briefly about powers and roots. So we say, to give a mathematical definition, for any positive whole number n, x to the n is equal to the product of x with itself n times. So for example, 3 cubed is 3 times 3 times 3, so 27. Another example, 7 squared is 7 times 7. I do the multiplication twice because of the 2, so 49. Now we say that if y is equal to x to the n, then x is an nth root of y. So basically I take x and hit it with itself n times, and I end up with y. This is what it means to be a root. So typical notation for this is what we call this radical sign, this square root or radical sign, with an n there to denote the nth root. If you don't see an n there, if it's just the radical sign, that canonically means square root. So n is equal to 2 in that case. Also nice is what we use as fractional notation. So we have a fractional exponent here. Now, the benefit of the fractional exponent we'll see in one of our upcoming examples. It makes it easy to do computations because then I can mix roots and powers. I can talk about, say, a number to the 3/2 power, where I first take a square root and then cube it, or vice versa, cube and then square root. The order turns out not to matter, as we'll see in an example. So let's look at a few things. Let's try to compute the 4th root of 16. So what is this asking for? This is asking for something so that when I raise to the 4th power, I get 16. So can we think of a number so that when I multiply it by itself 4 times, I get 16? Well, if you think for a minute, 2 works. 2 times 2 is 4, times another 2 is 8, times a 4th 2 is 16. But we have to ask, is this the only possibility, or are there other 4th roots of 16? And the answer is yes. If you think about it, -2 also works, because I'm multiplying by an even power here. -2 times -2 is 4, times -2 again is -8, times -2 again is +16. So -2 also works. This is very common with roots. Whenever you have an even root, square root, 4th root, 6th root, you'll typically have 2 solutions, plus and a minus. So sometimes this is written as plus sign, minus sign, 2, to denote that I consider both +2 and -2. Now, I'm not going to go into much detail about imaginary numbers, but in fact, there are also imaginary roots to this. We won't discuss that, but really, in some sense, there are 4 roots here to the 4th root problem. -2 and 2, and 2 other ones involving imaginary numbers. But we're not going to get into that. It's beautiful mathematics and very interesting, but it's a little bit outside the scope of this lecture. So let's look at another example. We have 3 to the 4th. So what does this mean? It means I'm going to take 3 and multiply it by itself 4 times. So not too difficult, I don't think. So this is 3 times 3 times 3 times 3. Maybe we can group this together and say that this is 9 times 9. And that's 81. So I think more straightforward to do this than to take roots. So here we have a tricky equation. It's going to involve roots and powers. So let's look at it. I want to solve for x. X to the 3/2 should be equal to 81. So what does this even mean? Well, I want a number x so that when I take its square root and then cube it, I get 81. And I can see that by writing this as writing it like this. Now, I can ask myself, how do I compute this? Well, what do I have to do? I have to do squaring both sides, so I get x cubed equals 81 squared. So some large number. And then how do I kill off the cubed here? Well, I take a cubed root of both sides. So I get that x is equal to the cubed root of 81 squared. And that may or may not be something that's easy to compute. Typically, you will use a calculator at this point to actually get a decimal representation of this number. Or for the CLEP exam, sometimes they'll just show you the solution like this, as a mix of roots and powers. So if you like, you can also write this in a rather compact way as x equals 81 to the 2/3 power. Again, we're mixing roots and powers here. The 2 in the numerator says I'm going to square something. The 3 in the denominator says take a cubed root. So you want to be a little bit comfortable with these mixed powers, where I have fractions in the exponent corresponding to roots, and also something in the numerator corresponding to powers.